Hi, this is a continuation of our discussion about concrete. As we have said, we can change the properties of concrete by adding admixtures. This is a classic example of a self-compacting concrete. This is a highly flowable concrete that requires no vibration. The flow slump is used rather than the slump. Flow slumps between 550 to 750 millimeter. That is, you have to measure diameter of this mix after removing it from the cone. Chemical admixtures are used that are high range water reducing admixtures and viscosity modifying admixtures. Also, the code actually gives us the specifications for the specified compressive strength of concrete. The value of this FC prime shall be specified in construction documents. It's very important and shall be in accordance with the following. A. Limits in table 19.2.1.1. As you can see, this table actually gives us two types of applications. In general application, your concrete can be normal weight and lightweight, and the minimum FC prime is equal to 17 megapascal. Of course, there is no maximum value for the FC prime here. But if you are using your concrete for special moment frames and special structural walls, that is, if you are constructing a structure within seismic areas, high seismic activity areas, then you need to use the minimum FC prime of 21 megapascal, either for normal weight and lightweight. The Philippines is actually divided into two seismic zones. Zone 2 actually has a very low seismic activity, so which means you can use general application for Zone 2. But take note, Zone 2 is only in Palawan and Sulu area. The rest of the Philippines is in Zone 4, which is with high seismicity activity. So which means we cannot use 17 megapascal as a minimum for the rest of the Philippines, but we need to use special moment frames and special structural walls, which should have a minimum FC prime of 21 megapascal. For the lightweight concrete, there is a maximum FC prime given, that is 35. Here, the limit is permitted to be exceeded, were demonstrated by experimental evidence that members made with lightweight concrete provide strength and toughness equal to or exceeding those of comparable members made with normal weight concrete of the same strength. Another to be satisfied is item B, that is durability requirements in table 19.3.2.1. And what is that? This is the exposure categories and classes for concrete. We have four categories actually: the freezing and thawing, that is capital F; the sulfate, capital S; in contact with water, that is capital W; and corrosion protection of reinforcement, that is capital C. If you look at every category, every category is also classified as different class depending on the condition. So, like for example, for sulfate, we have SO depending on the water-soluble sulfate in soil in terms of mass, or the dissolved sulfate in water in terms of ppm. So you can say SO, S1, S2, S3 depending on the dissolved sulfate. For the category in contact with water, class W sub O or WO and W1. So for WO, the condition is that concrete dry in service, concrete in contact with water, and low permeability is not required. So you can just say WO. But if the concrete in contact with water and low permeability is required, then you have to categorize this one as class W1. For the corrosion protection of reinforcement, the CO has a condition that concrete dry or protected from moisture. So that's the less of the class. Then C1, concrete exposed to moisture but not to an external source of chloride. C2, concrete exposed in moisture and an external source of chlorides from de-icing chemical cell, brackish water, seawater, or spray from these sources. Going back to the pressing and towing, we don't have it here in the Philippines, but of course, if you will be working in temperate countries, you have to consider this one. For FO, class FO, concrete not exposed to pressing and towing cycles. So you can use this FO in the Philippines. But F1 is concrete exposed to pressing and towing cycles with limited exposure to water. And then you can go to F3, F2, and F3. What does it mean? If we continue the table, you can see here that for, like for example, in the Philippines, we don't have pressing and towing, so we have exposure class FO. There is no maximum water cement ratio for that. And the minimum FC prime is 17. But if there will be pressing and towing, like for example F1, then your maximum water to cementitious materials ratio should be 0.55, and your minimum FC prime is 24 megapascal. So that's how we look into this table. If we proceed to the sulfate, if there will be no sulfate, that's SO, not applicable, but the minimum FC prime should be 17. But for S1, what is that S1? If there is seawater, or the quantity is around zero point 0.1 to zero point 0.2 or 150 to 1,500, or if it is seawater, automatic your minimum or maximum water cement ratio is 0.5 for S1. And the minimum FC prime should be 28. So you will have a higher compressive strength if you are building structures in seawater or near the seawater. First, you can also look for the additional requirements on the fourth column. You can read that one on yourself, and the limits on cementitious materials on the last column. Also for water, if there will be no water, that is W sub O, the maximum water cement ratio is again is not applicable, but the minimum FC prime is 17 megapascal. But if there is water involved, then your maximum water cement ratio should be 0.5, and the minimum FC prime is 28. So also for the cover CO, this is not, the maximum water cement ratio is not applicable to both CO and C1, but both of them has a minimum FC prime of 17 megapascal. And C2 has a maximum water cement ratio of 0.4 and minimum FC prime of 35. Again, you can look at the other column for additional requirements and the limits on the cementitious materials. That is for the durability requirements. Also, we have another item C, that is structural strength requirement. So when you look at these three requirements, limits on the table below, durability requirements and structural strength requirements, you will look into the most stringent requirement, and you can use the value for your FC prime. The specified compressive strength shall be used for proportioning of concrete mixtures in 26.4.3 and for testing and acceptance of concrete in 26.12.3. And this otherwise specified, FC prime shall be based on 28-day test. If other than 28 days, test aids for FC prime shall be indicated in the construction document. For the lightweight concrete, ECI actually says that we have to account for the properties of lightweight concrete. So thus we included a modification factor lambda in the multiplier of the square root of FC prime in all applicable provisions of the code. The value of lambda shall be based on the composition of the aggregate in concrete mixtures in accordance with table 19.2.4.2 or as permitted in 19.2.3. So you can look at the table to determine the values of lambda. First, lambda is 1.0 for normal weight concrete. If the measured average splitting tensile strength of lightweight concrete, that's FCT, is used to calculate lambda, laboratory tests shall be conducted in accordance with ESTM C330 to establish the value of FCT, and the corresponding value of FCM and lambda shall be calculated by the equation below. So that's lambda is equal to FCT over 0.56 square root of FCM, and it should be less than or equal to 1.0. Here is the table 19.2.4.2 for the modification factor lambda. So again, for normal weight concrete, lambda is just 1.0. For sand lightweight coarse blend, we have 0.85 to 1 depending on the Take note that linear interpolation from 0.85 to 1 is permitted based on the absolute volume of the normal course aggregate as a fraction of the total absolute volume course aggregate. For the sun lightweight, you can just directly use 0.85. And then lightweight fine blend 0.75 to 0.85, and all lightweight meaning all the mix, the sun and the course aggregate are lightweight. You can use directly lambda 0.7. Aside from that, we need to know the modulus of elasticity of concrete in compression. This is very important in our design. In this case, we have three ways of defining the modulus of elasticity. So as you can see in this diagram, the stress and strain diagram, we can use the initial tangent modulus, the secant modulus, and the tangent modulus. Here, the tangent modulus of elasticity, that's E sub t, is the slope of a line tangent to a point on the curve. And the initial tangent modulus of elasticity is the slope of the curve at the origin. Also, the second modulus of elasticity at the given stress is the slope of a line from the origin and through the point on the curve representing the stress. Note the second modulus is defined by using the point corresponding to zero point 0.4 Fc prime representing the service load stresses. Here is the definition of the modulus of elasticity for concrete in compression. So it's quite simple. If you have to draw the tangent line from the origin, that's the initial modulus of the concrete. If you draw a straight line at 2 points of the curve from the origin to a certain point, that's the secant modulus. Here it gives us the secant modulus at 0.5. Also, if you have to draw a tangent line at a point, then that is the tangent modulus here corresponding to the 0.5 Fc prime. Of course, the ECI gives us formulas to simplify our computation or determination of the modulus of elasticity of the concrete. ECI gives us these formulas. For values of the weight of the concrete between 1,440 and 2,560, that is in kilograms per meter cube, the ECI actually permits us to use this formula. Modulus of elasticity of the concrete E sub C is equal to 0.043 WC to the power 1.5 times the square root of Fc prime, and the result will be in megapascal. By the way, when you are taking the square root of Fc prime, do not forget that the square root of Fc prime, the unit is megapascal. This is quite unique. You don't need to convert the megapascal inside of the square root. The entire value of the square root of Fc prime is in megapascal. The other equation, if you are using or computing the E sub C for normal weight concrete WC is 2,320 to 2,400 kilograms per meter cube. You can just simplify equation 3 to make it equation 4. So A sub C is equal to 4,700 times the square root of Fc prime, and the result is in megapascal. Also take note that ECI Committee 363 proposed the following equation for high strength concrete because they were able to determine that high strength concrete has a different property compared to the normal concrete. So up to 83 megapascal, we can use this equation. A sub C is equal to 3,320 square root of Fc prime plus 6,900. Again, this is in megapascal. Also, there is an equation for the compressive stress and strain diagram. We have what we call the modified Hognestad, the first diagram, and the other one done by Todiscini. So as you can see, this is not actually the actual stress and strain diagram of the concrete. Hognestad and Todiscini actually wants to simplify the last portion of the curve because it's quite difficult to determine the values of this. So for Hognestad, he actually have drawn this diagram considering that is at a certain strain it will stop and then the stress will go down linearly up to 0.15 of Fc prime. While for Todicini, took the maximum Fc prime up to 90% of C prime and then it will go down using the curve Fc. Aside from that, we have other properties of the concrete which is very important if you do some modeling of the concrete. This is what we call the Poisson's ratio. Poisson's ratio is the ratio of the lateral expansion of the cylinder to the longitudinal shortening. If you remember, in physics, it's very simple concept, but it's very important. If you have a marshmallow, like for example, this cube, if you have to push from bottom and top, the marshmallow will shorten. So there will be some shortening of the marshmallow. But you may take note that the lateral portion of the marshmallow will expand. That expansion of the marshmallow compared to the longitudinal shortening is what we call the Poisson's ratio. The French mathematician Poisson actually observed that, and that property is very important for all the materials. For high-strength concrete, they were able to determine that the Poisson's ratio is 0.11. For the weaker grade concrete, it's 0.21. But you can use an average value of 0.16. On the basis of test of biaxially loaded concrete, Kopler et al. Report values as follows. So as you can see, these are above the average of 0.16. Normally, that's 0.18 to 0.2. But of course, you can always assume Poisson's ratio to remain approximately constant under sustained loads. We are talking earlier uniaxial strength of the concrete cylinder. That is if we have to apply only the loads in the longitudinal direction. But it's not always the case. You can also apply two forces, two major axes of the cylinder, or you can apply at three major axes, that is longitudinal and the two lateral axes. That's triaxial strength. If you look at this diagram, this is the strength of concrete under the biaxial stress. That is, we applied forces on the two principal axes of the cylinder. So as you can see, the bottom, if it is purely tension, see here at the third quadrant, this is purely tension, both sides. So your strength will be very low. But if you have to apply on the second quadrant, apply an axial force and a tension, this is the diagram. So with the other one, tension and compression, this is also the result. But if you have to apply both compression, FC1 and FC2, this would be the result. Take note that the result is greater than 1. That's the effect of biaxial loading. It will give us a higher strength compared to the uniaxial strength. Here is stress-strain response of the concrete accordingly. So you have this diagram, and normally as you apply the forces, like for example FL, depending on the value of FL, for FL of 550 psi, this is the stress and strain curve. For higher FL, you can see there will be also a higher stress and strain curve. That's the effect for biaxial strength. Also, you can apply triaxial strength. That is, you can apply on all the three principal axes of the concrete. Actually, here it shows that if you apply biaxial and triaxial strength, your strength will be higher compared to the uniaxial strength. Okay, so that's all for the corresponding properties of the concrete. We will still talk about the long-term property of the concrete in the next video. Thank you for listening.